Hey,
Hey, hello everyone. I'm very glad to welcome you all. My name is Vlad Bagnuk. I'm a community marketing manager at Developer Share. Follow us on social media networks to follow our job opportunities, activities, and future webinars. Also, a recording of this webinar will be available there. Links to our social media accounts you can easily find in our email. And now I give the floor to the speaker of our webinar, Nikhil Barthwal.
thank you, Ed, for the introduction. Hi, everyone. Very good morning. I don't know, we are from different time zones, so I'm assuming it's not morning. It's probably afternoon, evening, or something like that. It's a pleasure to have you here, be here. I'm going to talk about event-driven microservices today, and I'm going to be talking about how to implement the architecture pattern. So let me just start with sharing my screen. Actually, that's the window I need to share, and I can just go on a full screen mode. Okay. So, or maybe I should hold on. I'm just doing it. I can just share the desktop and then. View full screen, so I'll just play it. Okay, is it not working? Okay, so is it visible?
Yes.
Okay, wonderful. All right. So you're going to talk about patterns and practices for implementing event-driven microservices. Hi everyone, my name is Nikhil Barthwal. I'm a software engineer at Meta /Facebook, and previously I'd worked at Google and Microsoft. And this talk is based on my experiences working with microservices through various companies here, big and small, and some startups. So the agenda that I have today is I'm going to be starting with what are the motivations for moving from monolith to microservices. And then I'm going to be talking about the problems with microservices, more specifically, how the data is distributed across different services. And when the data is distributed across services, we need to talk about how to partition data. So here I'm going to be covering principles from domain-driven design that can be used to partition the data. Data scattered around services would basically talk about the problems that we have with scattered data. So we're going to be talking about distributed data. We'll move on to event-driven microservices. People think microservices and event-driven microservices the same. There are actually some differences, so we'll cover what those differences are. And then we start with various communication pattern across services, and then we go into some architectural patterns. So particularly, I'm going to be talking about event sourcing and command query responsibility segregation, which is more commonly known as CQRS. And towards the end, I'll be talking about what Sagas are and how they can be used. And obviously end with some resources. So let's start with monolithic, right? Very, very simple approach. You have one large code base that's very easy to develop. That's very easy to test, very easy to deploy. Everything is great about monolithic. In fact, it's a very good way of starting a new service. That usually monolithic is good when you build a new service, but the problem with monolithic is that it doesn't scale. So as the code base gets larger and larger, now you have several developers working on the same code base, so the development becomes slow. On top of it, every time you're going to be testing one big service, right? So it takes time to test that service. Deployment also is going to be slow. But I would add one of the advantage of monolithic is deployment is going to be easy because you don't really need a lot of automation. There's only one service, but it's slow. But the biggest problem with monolithic now is that it's too much of team interdependency. So for example, imagine that you have a team of 100 developers working on the same service, right? I make a change, somebody else might be impacted, somebody else makes a change, I get impacted. Up until then, it's fine. But you don't really have separate deployments in the sense I make a change, but the other person is not ready. I have to wait for that person to complete before the service can be deployed. This is where the problem with monolithic is that you can't deploy independent parts separately. You have to deploy the service as a whole because it's one service. So everybody is dependent on each other's schedule, and this slows down the development quite a lot. And this is a big drawback for monolithic, and that's the reason why we claim that monolithic generally does not scale. So it's a great pattern to start, but it's not a good pattern to end. You probably want to switch to microservice or something more towards the end. So microservices, what are microservices? Well, microservices is essentially what you do is you take this monolith and you divide it into different services. So it's an assembly of loosely coupled services. Now, what do we mean by loosely coupled? You have different services, but each of the service expose an interface, and all the interactions happens from that interface. So you don't really need to know the rest of the details. That's the reason why we say microservices loosely coupled, because you're only dependent on the interface. You don't really need to know what's happening underneath. If you change a service, the other service doesn't really have to change unless you change the interface. So it's basically, rather than having one big service, you have an assembly of small services. Smaller code base is easy to understand. It's easy to change. And now what you have is you have autonomous team. For example, you have 100 developers. Let's talk about the same example that we talked previously. And imagine that they are separated into 10 teams of 10 developers. Now, each one of those developers can work on a service of its own, and they can deploy it. And as long as interface does not change, they have independent deployment. They're not dependent on each other. And what this means is faster testing and faster deployment. So you can bring new features to your customers really fast. In fact, there's an interesting thing about microservices, that microservices basically borrows the concept from object-oriented programming, right? We'll talk about how it does in a detail, but essentially microservices borrows the concept from object-oriented programming, which itself borrows the concept from microbiology. And the reason is that object-oriented programming was actually invented by a microbiologist. I forgot his name. I think it was, I forgot his name, but he was actually a microbiologist by training. So what we have in a microservice? Well, what we have in a microservice is we have a service connected to a database. So there's one database per service. It's an anti-pattern to have more than one database per service, because if you do that, you actually have coupling. You don't want to introduce coupling. Some microservices may not have database. They could be stateless. Some may have database. That's okay. But you don't really have a database shared between two services. That's the thing that you don't want to do, because if you do that, what you're really doing is you're sharing the schema of that database with two services. So let's say first service wants to change that database. The second service also has to change. And that introduces coupling between the services. And that's an anti-pattern, because if you introduce coupling, you're going back to the same problem that monolithic has, that you're introducing dependencies. So that's the reason why you have one database. And when I say one database, you could have 2 or 3 databases. That's okay. But what you don't have is you don't have database shared across services. That's the stuff you don't want to have. And these are loosely coupled services. And when these are loosely coupled services, that reduces the team interdependency. So it obviously means that you could bring more features to your customers faster. So that's a faster innovation. Now, let me explain what connection microbiology has to microservices. Well, microbiology basically, microservices basically inherit, in a way, object-oriented programming. So when you think about object-oriented programming, what is that? Your software consists of these classes and these objects. And what these objects are is that each one of this object has a private state, right? The private variables. And then you have a public interface, the public, properties, methods, whatever. And you only interact with that object through its public interface. You can make any changes in the private part, nobody cares. It's only the public one that you actually care about. So that's the way microservices basically work, that they have their own shared database that you don't have, their own private database that you don't have access to. You only access the microservice from its interface. this concept of object-oriented programming actually originated in microbiology, because when you look at microbiology, human being or any living creature is a collection of cells, right? And what do cells have? Cells have a cell wall, and then there is a nucleus inside, and you don't interact with that nucleus. You just interact with the cell wall. So cell wall is your public interface, and nucleus is your private, whatever you call it, method, private variables, wherever all the action happens. So when the microbiologists saw a software, they saw software as a living creature. So they said, well, software can be made also in form of like these cells, which we now call as objects, and they have a public interface and they have a private interface. And then when we talked about web services, we also saw web services as a living organism. So we borrowed that concept of object-oriented programming and applied it to web services. So that's the connection between web services and microbiology. It's actually pretty interesting. I think it was Alan Kay. Yeah, now I remember Alan Kay, who was, unless you are a virus. Well, yes, that is true. Actually, technically, viruses are also the same thing, right? They are still single or multiple cell organisms. The only thing is that viruses have an intention to do some destruction as opposed to some constructive work. But hey, you could write a web service that can do some destruction also. So I think there's a big correlation between the two. You can have a quote unquote viruses service, hacking service, scraping service, and there are services like that. Anyhow, so the question is that now sorry, I think I skipped, yeah. So now the question is that we understand how, we understand that we have these, we have this data distributed across services. What we need to know is how do we create these service boundaries? So here we are going to talk about domain-driven design. So I'm going to introduce some principles of domain-driven design. I'll be very brief because domain-driven design itself is a big concept, big topic, and there are conferences. Forget about a talk. You have conferences basically for domain-driven design. So obviously I can't cover domain-driven design in a minute or two, but I'm actually going to be very brief. So basically domain-driven design, this is a textbook definition of domain-driven design. It's basically an approach to software development for complex needs. And what it does is it connects your implementation with a model. So you have a model of your system, and as the model evolves, the implementation evolves, and that model consists primarily of 4 important things. These are entities, 4 elements: entities, value objects, and then you have these entities that are these basically building blocks, and you have your value objects. The characteristic of value objects are that value objects are immutable. So they are basically, think of them as immutable structs in many programming languages like data classes, for example. And then you have a concept of bounded context. And bounded context says that in general, a sufficiently large software is too complex to be represented by one model. So there you have several models representing the same software. And each one of these submodels is basically bounded context. And then you have a concept of aggregates. Aggregates is essentially, and aggregates is probably the most useful one for our context, and I'll explain why. Aggregates is basically a collection of objects that can be treated as one. So these are the 4 building blocks of domain-driven design. And the way domain-driven design actually works is it's a layered approach. So you have a user interface, which is basically on the client side. Any software can be mapped into this multi-layered approach. Then you have an application layer, which is actually a very thin layer that manages a transaction. And then you have these domain objects. And these domain objects are basically your data classes, and they have methods attached to domain objects to do some kind of manipulation, but they're immutable. Bulk of your code is actually going to be on these domain objects. And then you have infrastructure layer or your persistence layer where you're handling all the database and everything. So this is basically, I would say, a minute or two summary of what domain-driven design is. Now, how can we use domain-driven design? So, yeah. So we're going to expand a little bit about aggregates, because for our purpose, aggregates is the one that we need the most. So aggregates is a collection of domain objects that can be treated as a single unit. Okay. And then one of this object is a root that we refer to this root. And in a way, it's like all it's a way like a private public. The root is the interface, and then the remaining objects are private, and all references would go to an aggregate root. A very common example is that when you're doing a shopping in a website like Amazon, right, you place an order, and your order would consist of some, I don't know, some grocery order. So you might have some apples, bananas, mangoes, whatever. For your purpose, your order is a single entity. Now, this consists of different domain objects, apple, mango, banana, whatever fruits you've ordered. But your order is a single entity that you refer to as an order ID. So order ID is the root, and all references to this order would only refer to the root of the order, which is your order ID. So that's a collection. That's an example of aggregate. And then what you can think about is that a domain model is essentially a collection of aggregates, right? Because a sufficiently large software system is too complex to be represented by one model. So you have these different submodels and they are collected together. And a domain model of a software basically becomes that collection. So we'll see an example here. Okay. So we'll just take our e-business example. You have an order service that places an order, right? So I'm using a UML notation. You have a customer service, you have a product service. And if you're modeling your e-commerce, you basically can, these will be your aggregates, right? Orders, customers, products. And what you do is you can map them all to a separate service. So aggregates basically provides boundaries for you for partition. Now, remember what we talked about microservice. Microservices is basically one system partitioned into a set of similar services. So the problem we had was, how do we define the boundary for that partition? This is where that comes from. Domain-driven design provides you a method to provide that boundary. Now, here, I would like to mention that there isn't a very unique way of separating a system. For example, I can treat order service and product service as one and customer service as another one. So in this particular example, I would have two aggregates. So you can always merge the aggregates. In general, you want to keep them as small as possible, but you don't want to really keep them very small, because if, you know, in a system you want microservices, typically you have few dozens to few hundreds, or in some cases few thousand microservices, but you don't really want a lot of services, because if you very finely grain your system, it's a headache for you to manage that system. So you have to come up with a sweet spot that you don't want a big service, but you don't want thousands of small services either, this middle path. And that becomes more of an art than a science of what that middle path is. And that's where you have to use your judgment, which reminds me of the fact that I was attending one conference and there was a guy from Uber who said that we had 7,000 microservices in production in Uber. And I was like, really? 7,000 sounds like a big number. And later on, I read some article that Uber actually thinks that they have too many microservices and they were thinking of merging these microservices, aggregating them. Good idea, but that's an extreme example of microservice where you fine grain your system too much. So you don't want to go too much, but you don't want to go too macro. And remember, it doesn't have to be, it's not a hard rule in the sense that if you were to separate order service and customer service, tomorrow you can merge them, you can service them. Obviously, it requires a little bit of work. Merging is usually more easy than separating, but you could do that. Anyway, so now that we understand that what are the strategies we can use to partition the data, let's move forward and understand what problems do we have with distributed data. Now, we have talked about the fact that every service has its own database, right? Which is great. But now we have this data scattered around all the services. So the first problem is, if you want to write, what do? We need data to be consistent. For example, let's take an e-store example that we go to a service, we go to the store, say Amazon.com, we make a purchase order. Okay, we purchase 10 dozens of apples. There's an inventory service that is basically managing the inventory. So it would say, well, 10 dozens of apple have been purchased, so it'll subtract. Great. There's a user service that manages that keeps track of all the orders. So that service has to be updated, saying that user Nikhil actually ordered 10 dozens of apple. There's a product service, there's a shipping service. They're all there. who are handling this order, they have to keep a track of the product, they have to make the shipment. Now imagine if the customer service, if the product service and user service, they all work fine and they make a change and they do the updation the way they should have done, but the inventory service does not write anything to the database, and they say, well, they for maybe there was a bug or the service crashed and they couldn't really write anything on their database. So on their inventory, they still show that apples are still there in the store. In reality, they are not, they have been shipped. That's going to be a problem, because the next time you order apples, your inventory service would say, we still have apples on the store, but in reality you don't, and the shipping service would not be able to do anything. So this is an example of data consistency, right? A change or an event in the system, we'll talk about an event, but an event in the system would trigger a series of changes that needs a data updation across multiple services. What if you have, and in a monolithic, you don't really have that problem because you only have one database. If that if service crashes, right, you know something has gone wrong, you can fix it. But here, because you have functionality scattered around, say, 20 different services, you now have a problem, because you could have something like a partial failure. Some services work, some services don't. So data consistency is one big problem. The second big problem is, how do you query that stated data? Now you have data put across different services. You need to do joins, something like that, because you don't really have one single way of one table where you can query. So these are the problems that we have with distributed data. How do we fix them? We can't use ACID transactions normally in this case, because look at this query. It basically is a simple query that gets some address from customers at some price and then inserts into order and commits a transaction. So let's say this is an order service making this SQL transaction. The problem here is that there are two databases that it's talking to, two tables in this case, the customers and the products. The customer is private to customer service. The product is private to product service. So how would you make this transaction? Where will this run? Because you don't have these databases connected, right? There'll be customer service will not have access to product. Product will not have access to customers. So we have a problem. Typically, you could use a two-phase commit, which guarantees a consistency, but it has its own problem. Coordinator is a single point of failure. Not to mention that latency is important and it's very chatty. So you have O(n) square retries, 4n messages. One of the things about microservices is that they have to act fast, right? You want fast throughputs, and locks would decrease the throughputs. On top of it, you have the cap theorem. We'll talk about cap theorem in details, but you have the cap theorem that basically impacts your availability. So that is the reason why you actually cannot use two-phase commits. So this is where the problem is. So we have explained what the problem is. Let's go into the solution. Now, before we go into the solution, I want to introduce a concept of eventual consistency. So we have mentioned cap theorem. What cap theorem, for those who don't know, is it says you can't have consistency, availability, and partition together. You could have two, but you can't have all three. That's a limitation for cap theorem. So partition is important. Partition is kind of de facto because you're operating in a distributed environment. So you have to have it. Availability is often very important because if your services aren't available, you're going to lose customer. Imagine how much transactions Amazon website gets every second. So even 1 second downtime can cost them thousands of potentially millions of dollars. So that's why availability is something that we usually would not make a sacrifice on. Of course, it depends on application, but generally that's the case. Well, we can deal with consistency, and we replace consistency with eventual consistency, and we solve this problem. What is eventual consistency? Eventual consistency says that your system will not be consistent immediately, but given sufficient amount of time, it will eventually reach a state where it will be consistent. And that's the reason why it's called eventual consistency. Now, eventual consistency, the consistency here is when we say eventual, these events can happen within few milliseconds to a second, right? So it's not going to be like you're waiting for hours for system to be consistent. It's usually a second or two. It won't happen immediately, but it'll happen so fast that for all practical purpose, you actually do not have a problem. Sorry, I think somebody raised hand. I could probably stop for a question. Do you have a question? If you have, you can just put it on the chat. Do you have a question, Daniel and Heidi? Because I see your hands raised. Sorry, I didn't notice it before. Okay, if you do, just put it on chat and I'll pause and answer. But let's continue. So sorry, where was I? Okay. We were at, let's stop. Yeah, we were at eventual consistency. So what we're going to do is we're going to have event-driven microservices. Okay. So what is event-driven microservices? Event-driven microservices are basically microservices that respond to an event. And what event-driven microservices does is they have this unique architecture that they sacrifice consistency with eventual consistency by use of events. So what is an event-driven architecture? Event-driven architecture basically says that every time there's a change in your system, there's an event, right? You place an order, you cancel an order, you browse, they're all events. And there are listeners who get notified by these events. In this case, the listeners would be services, and they may take an action. And generally, event-driven systems are highly distributed because you have these different listeners, producers and consumers, as we call them, and they are loosely coupled. And they're often used for asynchronous flow of information. And we'll talk about asynchronous flow of information. There's actually a very common event-driven architecture, might sound like something new and fancy, but it's actually very common. For example, let's say you're boarding a flight, go to an airport, okay? In an airport, you have loudspeakers or that are making some announcements, and you have these customers on the airport floor. Think of all those customers as services. Okay, so we think about them as services, and they're all listeners. So every time an announcement is made by a producer, somebody making that announcement, right, the listeners listen. Those who need to act would act, those who don't need to act won't act. So let's say certain flight 123 is departing. If you're boarding on this flight, please make your way to the boarding gate. People who are on flight 123 would immediately go. People who are not on 123 would just ignore. So listeners get notified. Some may take action, some won't. It's a highly distributed system. You have all of these people at the airport. Is loosely coupled because the producer does not know who the consumer are, and consumers don't know each other, right? So there's no coupling between different people. You have different set of passengers. They don't know who they are. They don't know each other. And it's an asynchronous flow of information. So in this case, the producer makes an announcement. He has no idea who the listeners were, what action they take. He just makes an announcement. He doesn't even know if the listener actually listened or ignored him. So that's an asynchronous. In real life, we have these architectures where we have these services connected to an event bus. The most common event bus being used today is Kafka, right? So Kafka, you have producers, you have consumers, and you have topics. I put a message on that message bus to a topic. People who are subscribed to that topic would read that message, and people who are not subscribed to that topic would ignore that. As a producer, I do not know who these services are that are subscribed to that topic and what action they have taken. I just put it. My job is just to put that information in the message bus and I'm done. So that's how event-driven architecture works. And this is in real life, event-driven microservices work the same way. That they have these different microservices. They don't know anything about each other because they are loosely coupled. You have these events in the system. The services would inject this event in a service bus, or they may contact, and we'll talk about the communication pattern later on. And the receiver may take some action. So let's talk about communication pattern. So we have these events. Sometimes what happens is that these events are directly messaged to the services, right? The concerned services. So order service might talk to customer service, might talk to producer service, usually REST calls, right? The benefit of direct messaging is that it's a very easy implementation, right? There's no event bus, there's nothing like that. You just talk to the relevant people directly. There's a better error control. It's a synchronous communication. Synchronous communication, there's a better error control. So if something goes wrong, you immediately get notified that, because the other person is actually going to be responding. So request response pattern. That gives you a better error control. But the problem now is that it's difficult to scale. Imagine if you have a new service that needs to be listening, that needs to listen to order service. You have to introduce this service, right? You have to inform order service that there's a new service, also send the message here. So it increases the coupling. And the more and more services you add, the communication pattern is way too complicated, that it's very, very difficult to understand what's going on. Imagine if you have 1,000 services communicating with each other, you will get a headache if you try to map who talks to who. It's just not scalable. And then you have a via message broker, right? So services just send a message, whosoever is interested, they can read that. Imagine if in the same case, you have a new service that is coming in, it just goes to the message broker and it subscribes to a topic. Every time order service makes a new event is generated into the message bus, the new service just reads it. So in this particular case, order service does not need to know about this new service, right? So that is why it decreases the coupling. It's a very scalable way, but it requires broker, right? And obviously we saw the drawback that there you have better error control, here you have less error control. So that's another problem. So typically what you do is in real life, you use both. So we take these services, we divide them into three parts. We talk about tier 1 services, the services that interact with customers. They are generally request response or synchronous in nature because they have error control needed in them. But that's going to be a small part of your services, probably 5% of them. 95% would not interact with customers. Then you have the rest of them would be event-driven asynchronous. So tier 2, tier 3 would go into event-driven, which have no impact for the customers. So that's how typically real-life systems would be designed. Now, we have talked about events. So what is event sourcing? Well, the problem here is that you have these events, you have a lot of these events, you respond to these events, you write something to your database. Event sourcing is basically an architecture pattern that says that state changes are a sequence of events, right? So your state is basically a collection of events. You store these individual events and you build a state. And you store these events, you can obviously roll back in a particular time because now instead of having a single state, your state consists of a collection of events. So you can just roll back in a particular time and say, well, what was my state right now? This is the event that caused it. Event sourcing in some form has been used since ages. The most common example is bank ledger, right? In bank ledger, your state of the system is basically your account balance. What's my total account balance? And what is your total account balance? Every time you make a transaction, you imagine you open up an account, you have an initial balance of 0. You deposit some money, you withdraw some money, you deposit some money, you withdraw some money. Your total balance is basically a sum of all the transactions. If every deposit is like a positive number, I deposited $10, and every withdrawal is a negative number, I withdraw $5, and you add all of these, you get your total account balance. So here, think of every transactions that you do in a bank as an event. And your state of the system, your total account balance, is basically a sum of all of these transactions. So you aggregate all of these events, you get your state. Another example is version control, right? Every time you're developing a software, your state of the software is your current source code. And what does it consist of? It consists of the commits that you have made. So every time I make a change, I commit to my Git. Every time I make a change, I commit. My total at any given point of time, I can actually look at my source code as a set of all the commits that I've made previously. So I'm storing the state as a set of events. And here also I can roll back in time and I can see what was my source code 3 days back, what was my source code at this particular time. So it enables you to go back. So that's what event sourcing does. Event sourcing basically models the state as state changes. There are benefits of it, and obviously there are drawbacks of it. We'll talk about that. Now, one of the problems that event sourcing has is that when the system is running for a very, very, very long time, what happens is that every time you have to build and state, you actually would have to play back all the states. So imagine you want to know your total balance. Your account has been in existence for last 10 years. Every day in 10 years, you were making multiple transactions. So now you want to know an account balance, you would have to go back 10 years and sum all of these events together, which is quite tedious and inefficient, and it takes a lot of time. So there's an optimization technique that it does is it's called what is called as a snapshot. So it will create periodic states, and then every time you have to play back the state, it will basically look at the last snapshot and play events from that. For example, let's say that in the bank account example, you can commit multiple transactions a day, but every day on the end of the week, weekend, when there's a Sunday and there is no commits happening or whatever, the system will basically sum all the transactions on this week and would give you what the current balance was at the end of the week. So let's say if I want to know my current balance today, there's already a snapshot last Sunday. So I just have to play the events from Sunday and not from 10 years. So that's how it works. So there's a snapshot taking periodically, and then the events of system is state is being constructed from the last snapshot. Another thing about event sourcing is that you can create multiple views out of it. So here's an example of, let's say, Facebook. Okay, you have an event. You get married. That's an event. You place that event. There are 3 different components on your website. You have a timeline, you have a photo, and you have a personal info section. Your photo says you got married. It doesn't do anything unless you put pictures of marriage, which you should. Then your personal information section, where it says single, it will change to married. So status update. On your timeline, it will say, well, XYZ got married this day. So the same event, marriage happens, 3 different apps create 2 different views, and one app ignores. So there's different application that will process this event would do it differently. The same thing happens when you post a photo. Your personal info section does not care. Your timeline, the photo will appear. Your photo app, the photo would appear. So the same event, you post a photo, different services would basically react to that event in a different way and create a different view. So that's the advantage of event sourcing, that you could have multiple views. So let's talk about the benefits and drawbacks of event sourcing. Some of it we have already covered. One, you have a very accurate audit log, because you can go back in time and you can basically see what your state is. You can change your state. So imagine that on a credit card, you're using your credit card and you discover 1 week ago there was a transaction on that credit card that doesn't appear to be legitimate. So probably somebody stole your credit card, used some transactions, you go to the bank says, fine, we'll remove that. What does bank do? Bank would unwind all the transactions that you have done, take that one transaction that is bad, and then replay all the transactions. So what you have basically done is you have done an unwind and then you have a rewind. Okay, you can do these, you can combine these events, you can mix and match, because you're storing each one of these events separately. So it's a very accurate way of logging. You can do auditing, you can do temporary quitting, and we already saw the same application can process same event with different views. But the problem is it adds complexity. Okay, there's no strict consistency. Remember, we talked about it. Every time you're constructing a state, the events have to be played, and different services might process different times. So it may take a time for them to bring the state up to the order. So we look at the previous example of Facebook. You post a photo, the timeline will process it, the photo app would process it, but they may not process it at the same time. They will eventually come to the consistent state, but it may not happen at the same time. So there is no strict consistency. But then this is what we are talking about, event-driven microservices, right? Event-driven microservices don't really care about consistency. They just care about eventual consistency. And this is the reason why event sourcing is fine for event-driven microservices. We also talked about longer boot times, but then we looked at how snapshots can actually help. So now that we have talked about event sourcing, Let's talk about command query responsibility segregation, or CQRS as they call it. It's actually a must for event sourcing. And what CQRS basically does is CQRS separates read and write into two separate services. So you have basically, you introduce the concept that there is a command and then there's a query, right? Command and query are two separate things. A query will just query a state, but will not make a change. And then there is a command which would not return anything, but it will make a change. And command and query basically are separated with each other. And this gives you more scalability. So you can read a lot. Now, why is it must for event sourcing? Remember, we talked about it that we have a state that is going to be reconstructed from events. Where is that state going to be reconstructed from? Well, you have all of these events, your database is storing these events, but you need to develop a model from where you can query. So these events are read into the read service, which creates a model, and then you can query that model. So that is why read is going to be separate. And write would obviously has a command model that will just write to the database. So you have read and write separated. If you don't have event sourcing, you don't really have to worry about it. But in event sourcing, there is no way to really read or make a query to the system because you don't really have a state ready-made build. It has to be built from events. So read service is the one that is actually going to be built. This is the reason why CQRS is actually must for event sourcing. So what are the benefits and drawbacks of? Well, if you're using event sourcing, you have to use it. It also has a benefit that it improves the separation of concerns, and you can create multiple scalable views because here you could have like 100 read services and 1 write services, right? You could create different views for the same. We already looked at the example of Facebook, how it creates different views from the same set of events. So you could actually do that, but it increases the complexity. There could be some code duplication because if you have multiple models, you have multiple code that is going to be reading, building the same model. So you could have code duplication. You also have some replication cap because event has to be written to the database. The read service has to pull that event. It has to construct a state. So there's no strict consistency in CQRS. But again, event sourcing and eventual microservices, that's a drawback that we accept. So that's usually not a problem. So now we go back to Sagas, and what Sagas basically would do is we have talked about the problem of distributed database. We've talked about, remember the two problems with distributed data. You have a problem number one, which is how do I query? And you have problem number two, how do I write? Now, CQRS would basically solve this problem of how you query the data. Now we are going to solve the problem of how do you read. So Sagas, what Sagas is, it's actually based on a 1987 paper, which was initially for a single database running on a single node, but then we have distributed systems, and in distributed systems, you could have partial failure and we can have asynchronously. So Sagas, we adopt to distributed systems that can deal with asynchronous nature and partial failure. And what Sagas basically is it's in a way a workflow. So let's say every time an event has happened, how would services react to it? So service one would, there's a transaction, right? An event happened, a service would read that event and it does certain action and it would create another action and so on. So there's a transaction, and every transaction, if you think of every event, reaction to every event as a transaction, it has its own counter or what we call as rollback transaction. And this logic must be included in the service. So we'll see an example, it becomes more clear. So let's say that you have a transaction with T1, it creates T2, creates T3. But what happened was T2 to T3 failed for whatever reason it failed. So then it creates a rollback transaction. So it will undo the changes that T1 has. So basically what you're doing is every time a workflow either will be complete or will be complete failure or complete success, but it would not happen in an eventual manner. It will be like a workflow. So you have the same benefit that you have in regular SQL queries or regular single databases, that you have an atomicity of a commit, right? It's a it's a complete failure or it's a complete success. You don't really have partial. So you're basically mimicking that atomicity in a service, except that in this particular case, it would happen in an eventual gradual manner as opposed to a single transaction. So that's what Sagas would do. Now let's actually see an example of how it works. So we talked about Saga, long-running compensation using compensation action. Imagine that you deposit a check, right? So let's say I am transferring, person A is transferring money to person B, and person A transfers $1,000. So how does it work? Well, this deposit check would initiate the Saga. Person A would look at it. Okay, person A wants to transfer person B $1,000. Does person A even have that much money in his account? Say yes, good. Then that money is withdrawn from person A, and then the deposit service would actually go to the person B's account and deposit that money. And several things could go wrong. Maybe person A does not even have $1,000, in which case it stops right there in the first place. Let's say that you withdraw the money, and while you're depositing, person B basically closes his account. So the money has nowhere to go. So it creates a rollback transaction that says, okay, what was the opposite action of deposit? Withdraw, deposit. So $1,000 would be withdrawn from person A's account. The withdrawal service will try to send that money to the deposit service. The deposit service would say this account has been closed. Withdrawal service will start its rollback option, and this money would basically go back to A's account. So either money is being transferred or money is not being transferred. If you don't have a compensating action, what you would have is A has $1,000 have been removed from A's account, but nothing is deposited to B's account. So you basically A has lost money. So that's an example of Saga. Now, Sagas basically have some kind of, it's a drawback that it does not have isolation, right? So it has atomicities in the sense that all transactions are executed and they're all compensated. It is consistent because each one step would trigger the second one trigger the third one. So that's all good. There's consistency, there's durability. Message brokers guarantee, the messages are being delivered, there's an acknowledgement, so there's durability, but there is no isolation here. So you have to take countermeasures that treats these isolation into effect. So that's why these are not strictly ACID transactions. Now, when you talk about Sagas, you're talking about some kind of distribution on who's going to start compensating action. Some decision making has to be done. There are two modes of those decision making. There's a choreography and there's an orchestration. Choreography means distributed decision making. Services make their own decisions. Orchestration means central decision making. So we would basically one central authority would make all the decisions. So there are drawbacks of both. This choreography says it's simple, right? Service would make its own decision. So that's distributed. There's loose coupling. But it also somewhat increases the coupling of the components because you have to know, the components have to know how the services would react, what are the rollback actions, what to do if something fails, because there is no central authority. You also could have a cyclic dependency. A would do something to B, but B would do something to A because there's no central authority that is dealing with these changes. And then you have orchestration, right? Centralized coordination. It's easy to understand and implement, and it reduces the coupling because now the components of the different system can interact with each other. So there's no significant drawback of orchestration. So usually in most practical cases, orchestration is how you make the decisions. But again, every application is different. So you have to really look at orchestration could also be that your central decision maker is a single point of failure. So you have to really look at problems for it. Don't just take my suggestion for granted and just use orchestration everywhere. It depends also on your problem. So we are reaching towards the end. I want to give some resources. So we have talked about domain-driven design. This is the more popularly known as Blue Book, right? This is Eric Evans, was the founder of domain-driven design. We have talked about microservices a lot. Sam Newman has an excellent book on building microservices. There's a second edition for this book. This is actually the first edition. And then Chris Richardson has a great book on microservices that talks about Sagas, orchestration, choreography. And I have some of the links. This is Chris' website, so he talks about Saga. There's another website. Twitter uses this. I don't know if they still uses it, but Katie had a talk on distributed Sega. So there's a link here, and then this is a talk to Eric's. This is a link to Eric's talk where he talks about domain-driven design. We are almost towards the end, so I'm going to actually do a little bit of a summary. So we understand that microservices enable faster innovation because it reduces the coupling, right? But microservice has their own database. We have to basically divide a service, divide the functionality into smaller parts. So domain-driven design can be used to define these service boundaries. But when you have these services, each microservice has a single database. Data is distributed across different services, which creates a challenge. So we use event-driven architecture to solve this problem. We sacrifice consistency. We use patterns like event sourcing and CQRS, and then to maintain data consistency across services, we use Saga. That's all. Does anybody have any questions? So I'll actually stop here. This is my contact details. So if you have questions later, if you have questions now, I'll be happy to answer. If you have questions later, my contact details, feel free to contact me anytime.
I have a question. Yeah, it's about the interactions between microservices. If we briefly distinguish between mutating operations and a pure information gathering. So let's say service A receives a message, and in order to carry out its work, it needs some information that it does not have. After all, I mean, it's very difficult not to have that kind of situation. And the information originates from service B. So there are different kinds of ways to implement this. Of course, one is using a request response, synchronous, perhaps an HTTP request from service A to B to get that information. Another would be to implement that with totally asynchronous messaging as well. So send out an information request and then you receive it. Obviously, this is more difficult, or much more difficult to handle. And then there is another pattern that I think is very elegant, and that is where it shines the most is if there is lots of information that's needed. So perhaps for A to carry out its work, it would have to issue thousands of requests to service B. Obviously, that is suboptimal. So then if that information is published by service B, service A can just build up its own representation of that. So I like to describe it as an integration modeled on event sourcing, basically. And my question is, have you ever? I would personally refrain from doing the pure asynchronous interaction to avoid the request response style interaction. If you know that the information can be gathered from service B, simply because if you use CQRS and have read models that are scalable, absurdly scalable, and stuff like that, it should be preferable in most cases, at least. What's your spontaneous comment on this?
I think it's a fairly general question. So you kind of answered your question yourself, because you said you would avoid purely asynchronous. So yes, in real life, you use a mix of request response and asynchronous. You don't really have one or the other. So depending on considerations that you have, how you implement, in this particular case, request response pattern would be way more simple, right? Or what you could also do is when the first service sends a message, it actually takes that message from service B, and it has everything in that event that it needs. So you don't really need to request that information from service B. You can attach it to the original event.
Yeah, that's some kind of routing, command routing. And enrichment.
Yes, exactly.
Yeah.
You can do the routing part of it.
Yeah,
So,
I have a hard time to accept that in many cases because it seems so ad hoc. It's like, okay, so this is a command for service A, but somehow it ends up in service B, and service B somehow magically knows that I should enrich this command, which is not aimed for me at all. And it's very easy to see how that can get absurdly complex.
yes, that is true. So yes, it is kind of random. So these are two alternate ones. In this particular case, I would say just go with request response.
Yeah, thanks.
Yeah. Obviously, request response has a bit of an issue with scalability, but you can have victim paths of service B and read model. You also mentioned that, FYI, that your read model is quite optimized, then you won't have that problem.
So this is just a more of a social question, because I have been acquainted with event sourcing for a very long time, and read lots of articles, so I've got mentally acquainted with it, and now I use that in production as well. And I'm a great fan of event sourcing. I think it's a brilliant idea. But often, if you talk to people who are not as acquainted with it, they react with aversion. Say, that seems so absurdly complex. Why on earth would you like to do that and evolve the events and everything like that? So how do you see it being adopted by developers?
I think people adopt it a lot, but sometimes they don't realize that they're adopting it. Like, event sourcing is not a new idea. Bank ledger, I talked about bank ledger, right? It has been there for, I don't know, 1,000 years, right? It's just a fancy name to something that you have. So I do think that event sourcing is used a lot, but sometimes people don't really realize that they're using it. And there are different ways of using it. Again, in real life, you have to look at the problem and find the best solution, right? So there is no one pattern that you can use. You could have a fixed state, you can have event sourcing, or you could have both, right? So I think real life systems, they tend to be very hybrid, and people do use event sourcing. They just sometimes don't explicitly call it event sourcing, and sometimes they don't realize it that they are using it event sourcing, but it is actually event sourcing.
Yeah. No more questions from me.
Okay. I have a message here from Adil, and it was nice. Thank you. I'm glad you enjoyed it. Hope that helps. Any other question? Do we have any other questions? Okay.
I think it's all. So thank you, Nikhil, for the webinar. The webinar was very informative. Thank you.
Thank you very much. It was a pleasure.
Thanks, and bye.
Bye-bye.
Bye.